This video I'm going to continue on the part of supremum and infimum. So let's start with the example of the interval negative infinity up to the 1 in which is not included. And we claim that the supremum exists but the maximum doesn't exist. Also, for the supremum of S, it is equal to 1, which does not lie inside this interval. To prove that the supremum is equal to 1, we have to prove that it is an upper bound. Well, but it is obvious from the definition of this interval that 1 is an upper bound. So we have to prove another statement. We suppose that there exists a mu such that mu is more than 1 and mu is still an upper bound. And we choose an x which is equal to mu plus 1 over 2. And from this picture we see that it is the midpoint between the point 1 and mu. And from this picture we obviously see that mu plus 1 over 2 should be smaller than 1. So mu plus 1 over 2 should lie inside the interval negative infinity up to 1. And this is from the definition of this interval. And from this picture we also see that mu plus 1 over 2 is bigger than mu. But remember that mu is an upper bound, and there is nothing that can be bigger than mu. And therefore, this is a contradiction to the fact that mu is an upper bound. And therefore, the negation of our statement is that for all mu which is an upper bound, mu is bigger than or equal to 1, either 1 is the least upper bound. So from the definition of supremum of S should be equal to 1. And sometimes the statement of the supremum is very difficult to prove, and we need another formulation in order to make ourselves more convenient. And therefore we will introduce another formulation for the supremum and infimum. So here is the formulation. We let L equal to the supremum of S, and L equal to supremum of S is equivalent to two statements. First of all, L is an upper bound of S, and for all epsilon greater than 0, there is an x0 which is lying inside S, such that L minus epsilon should be smaller than x0. And first of all, we will prove from the left hand side to the right hand side. We suppose that L is equal to supremum of S. By the definition, L is an upper bound. So if L minus epsilon, then it is no longer an upper bound because it is smaller than L. And therefore, there is an x0 inside S such that L minus epsilon should be smaller than x0. And another part is from the right hand side to the left hand side. Well, again, to prove that it is an supremum, we need to prove that L is an upper bound and L is the least upper bound. Well, from our assumption that L is an upper bound, we are done with the first statement. And we have to prove the second statement. And as usual, we will use the proof by contradiction. And I let L prime to be another upper bound such that L prime should be smaller than L. We subtract L prime to the right hand side, we get that L minus L prime should be greater than 0. And as L minus L prime is a positive number, and our second statement here is true for all epsilon greater than 0. And therefore, we are legal to choose epsilon to be L minus L prime. But L minus epsilon is equal to L minus bracket L minus L prime. And after the cancellation, we get that it is equal to L prime. But remember that L minus epsilon is smaller than x naught for some x naught inside S, and therefore our L minus epsilon this time is L prime, and therefore L prime is smaller than x naught for some x naught inside S. Well, this is a contradiction because remember that L prime is an upper bound by our assumption, but it turns out that there is something that is bigger than our upper bound inside S, and this is indeed a contradiction. And therefore, the negation of our previous statement is that any upper bound L prime should satisfy the relationship L smaller than or equal to L prime. And remember that L, we have proved that it is an upper bound. And from this statement, we see that L is the least upper bound. And therefore, by the definition of supremum, L is the supremum of S. Similarly, we can formulate the infimum in the same approach. And the statement is as follows. If L is the supremum of S, this is equivalent to two statements. First, L is a lower bound of S, and for all epsilon greater than 0, there is an x naught such that x naught is smaller than L plus epsilon. And how can we prove so? We do not have to do the dirty work again, because we have proved that the infimum of S is equal to negative of supremum of negative S. And therefore, if we let L equal to infimum of S, then negative L is equal to supremum of negative S. So, by the definition of supremum, negative L is an upper bound of negative S. And therefore, L is a lower bound of S. And also, negative L is equal to supremum of negative S is equivalent to for all epsilon greater than 0 that exists x naught inside negative S, such that negative L minus epsilon should be smaller than x naught. This follows from our previous formulation for supremum. And as x naught is inside negative S, there is a y naught inside S such that x naught is equal to negative y naught. This is because negative S is just taking the elements of S, the negative sign, and therefore we get that it is equivalent to negative L minus epsilon smaller than negative y. And if we put everything back to position, we get that L plus epsilon should be greater than y naught, and this is essentially our statement 2. This is the end of the video about the supremum and infimum. See you in the next video.